Hello, this is Omprakash Yadav. Today I am going to start minimum number of teeth on the pinion and gear to avoid the interference. So, while discussing the interference in the involute tooth profile, I have suggested one method to avoid or to reduce the interference, that you increase the number of teeth on the pinion and the gear. So in that way also interference can be avoided. If by increasing the number of teeth on the gear or pinion interference can be avoided, then what is the minimum value? What is the minimum number of teeth which must be on the pinion or on the gear so that interference can be avoided? So now I am going to see that how many minimum number of teeth should be on the gear and on the pinion to avoid the interference. So minimum number of teeth on the pinion and the gear to avoid the interference. Okay, let us understand this figure. Here I have taken the gear and at the bottom I have taken the pinion. I have taken pinion as a driver and this gear as a driven. So let us see that this is the common tangent at the pitch point. This is the pitch point. So this is the common tangent at the pitch point and this is the common normal at the point of contact. You know that common normal at the point of contact is also common tangent to the base circle. So this is the base circle of gear. Look at here. This is common. This is here tangent and this is pinion. So this is the base circle of pinion and this is tangent here. Okay. So this is a common normal at the point of contact and this is also common tangent to the base circle. Common tangent to the base circle. So this is the base circle of gear. This is base circle of gear. This is the addendum circle of gear. Similarly, this is the base circle of pinion. This is the base circle of pinion and this is the addendum circle of pinion. Look at here. This gear is rotating with the angular velocity omega z in this direction and this pinion is rotating with an angular velocity omega p in this direction. Okay. Now I have discussed while discussing the interference in involute gear tooth that you increase the addendum circle radius. You increase the addendum circle radius. So now I am increasing the addendum circle radius of this gear and pinion both. So point of contact will move here towards the point M and the end of engagement will move towards the point here. Okay, so when you are increasing the addendum of gear and pinion both, then addendum circle of the gear first touches or crosses the limiting point of interference. Limiting point of interference, who touches first? So tip of the gear, that is addendum circle radius of the gear crosses the limiting point, limiting interference point. Okay. So from this figure you can see that addendum circle radius of the gear is touching the limiting point M, that is here K is the start of engagement. But look at here, at the same time I am increasing in a similar amount the addendum of the pinion. So they have gone only up to this point. This is the end of engagement. They have not reached up to the limiting point N. So conclusion is that first interference start at the tip of the gear and flank of the pinion. Flank of the pinion. So by considering this concept, minimum number of teeth should be derived. Okay. In some of the book, they are taking this L at the point of N, but that is not the correct situation. That is wrong concept. Okay, that should not be there. If the interference has started at one place, means they have started. We are not going to wait that when this will start at both the places, then I will tell that interference has started. That is not the scenario. If the interference has started at the tip of gear and the root of pinion, so they have started. So just to avoid the interference, this is start of engagement you are looking that has come up to the limiting point M, but this end of engagement is not going to the limiting point M. So that is here, that can be seen when you will draw the exact diagram. You increase the addendum of both gear and pinion by same amount. Also you can see that this addendum of this both are same. This both are same, which is happening in actual case. Okay, let us see that this is the addendum circle radius of the gear. This is the pitch circle radius of gear, and this RB. Here this is the base circle, so this RB is the base circle radius of the gear. RB is the base circle radius of the gear. Similarly, you can see from here this small RA is the addendum circle radius of the pinion, and this small RA is the pitch circle radius of the pinion, and this RB is the base radius of the pinion. Acha, let us do some mathematical calculation. Look at, you join this point O2M. You join this point O2M. Now, you see that this angle between the common tangent and the common normal at the point of contact is known as the pressure angle phi. If this is the pressure angle phi, then this will be the pressure angle also phi. This will be also pressure angle phi. So from here I have drawn the normal, that is O2n. From here I have drawn the normal, that is O1m. So this angle is phi and this angle is phi. Look at here. This is the pitch circle radius r, small r. That is this O2p is small r, and this angle is what? Pressure angle phi. So component of this r along this will be r cos phi, and the component of this along this will be this one Pn. That is what? Capital R sin phi. So this capital R can be resolved into two component, r cos phi and capital R sin phi. Look at here. Also you can see that this O2n is the base circle radius. So base circle of radius is also equal to capital R cos phi. So base circle radius of the gear is equal to capital R cos phi. Okay. Similarly, you can see for the pinion, this small r is the pitch circle radius of the pinion. So this O1p is a small r, this angle is phi. Again, this small r can be resolved into two components, that is r cos phi and this r sin phi. This MP is small r sin phi, and this is what is small r cos phi. Again, you can see that this O1m is the base circle radius of the pinion. So base circle radius of the pinion is equal to small r cos phi. Small r cos phi. Okay. Now you join this O2m. You join this O2m. Okay. So in the right angle triangle, this O2m n. In right angle triangle O2mn, so this O2m square is equal to mn square plus O2n square. O2n square. So same thing I have written here. Look at here. In the right angle triangle O2mn, O2m square is equal to mn square plus O2n square. Let us put the value of this. So look at here. What is this O2m? What is this O2m? This is what? Capital RA. Capital RA is the addendum circle radius of the gear. So I have put this O2m is equal to capital RA, O2m square, so capital RA square. Let us see what is the value of mn. So this is the mn. So this mp is small r sin phi, and this pn is capital R sin phi. So this plus this ka whole square. Same thing you can see here, that same thing I have written. Plus what is this O2n? Look at here, this O2n is capital R cos phi. So O2n capital R cos phi ka whole square. So capital R square is equal to capital R sin phi plus small r sin phi ka whole square plus capital R cos phi ka whole square. You expand this, then you are getting this. Look at here, from this and from this you take this capital R square comma, then you will get sin square phi plus cos square phi. Then this one small r square sin square phi. Then this one 2r small r sin square phi. So this can be extended from the formula a plus b ka whole square. So a square plus b square plus 2ab. Okay. So from this formula you can write this expression. Look at here. So this sin square phi plus cos square phi is equal to 1. So that becomes capital R square, and this is r square sin square phi, and this is 2 capital R small r sin square phi. Again, let us take capital square common from this whole. So what we are getting, this capital R square is equal to r square 1 plus small r upon capital R ka square sin square phi plus 2 into small r bata ke capital R sin square phi. Okay. Again, from these two terms, take small r bata ke capital R comma. So what we are getting is small r upon capital R. In the bracket small r bata ke capital R plus 2 into, you take also this sin square phi as a comma, as a out. So we are getting this sin square phi. Okay, we know that gear ratio capital G is equal to number of teeth on the gear बटा के number of teeth on the pinion. Also, this can be written as pitch circle radius of gear बटा के pitch circle radius of pinion. Okay, if you use this formula that gear ratio G is equal to capital T beta k small t is equal to capital R beta k small r. So small r beta k capital R will be 1 by G. So same thing here, 1 by G, 1 by J. So I have written here. So this is equal to this one. Okay, so capital R is equal to what? Under root this whole quantity. So this is R square. So that is outside. So capital R under root 1 plus 1 by G. Inside the bracket 1 by G plus 2 into sine square phi. So maximum, if you know the addendum circle radius of the gear, you know the p circle radius of the gear, then you can calculate what is the maximum addendum of the gear. What is the maximum addendum of the gear? Look at here. So maximum addendum radius is up to this point here. So from here to here, and this is what from here to here up to this is the p circle radius. So what is the addendum from here to here? So radial distance from the pitch circle to the addendum circle. So this will be capital RA minus capital RA minus capital R. So this one capital RA minus capital R. So maximum addendum of the gear AG max, G for gear and the max is equal to capital RA minus capital R. Put this value of capital RA here. So I am getting this. Take this capital R from this both outside. So I am getting this one. Here I will get minus 1. I know that pitch circle radius of gear capital R is equal to m into capital T divided by 2. Let us put the value of capital R here. So what I am getting that maximum addendum of the gear AG max is equal to m into capital T divided by 2 under root 1 plus 1 by Z inside the bracket 1 by Z plus 2 into sine square phi. Then outside this root is minus 1. So this is what the maximum addendum of the gear means. If addendum of the gear will be more than that, then the interference will occur. If the addendum of the gear will be less than that, then there will be no interference in the gear. So to avoid the interference, actual addendum should be less than this AG max. So let the actual adopted value of addendum of the gear is AG times the module. AG times the module. This AG is the addendum coefficient of gear. So let us assume that actual adopted addendum of the gear is equal to m into AG. So this is the equation number 1. This is the equation number 2. So to avoid the interference, this maximum addendum should be greater than or equal to the actual addendum, or this actual addendum should be less than or equal to the maximum addendum. So let us put the value. So maximum addendum I am putting here and actual adopted addendum I am putting here. Now this module from both sides can be cancelled out. Then you solve for this capital T, number of teeth on the gear. So what we are getting, this T should be greater than or equal to 2 times AG divided by root 1 plus 1 by Z inside the bracket 1 by capital G plus 2 into sine square phi. Outside the root this is minus 1. So this number of teeth on the gear to avoid the interference should be greater than or equal to this. So what should be the minimum number of teeth? So if that number of teeth on the gear should be greater than or equal to this, so what should be the minimum number of teeth on the gear? So minimum can be equal to this. So minimum number of teeth on the gear, capital T minimum is equal to 2 times AZ divided by under root 1 plus 1 by Z inside the bracket 1 by Z plus 2 into sine square phi minus 1. Outside the root is minus 1. So minimum number of teeth on the gear can be calculated from this formula. Okay. So what is actually happening in most of the local book? They are calculating first minimum number of teeth on the pinion by using some similar formula, but that is wrong. So you have seen that first tip of the gear reaches the limiting point of interference. Okay, so you have to do in that way. First you calculate minimum number of teeth on the gear from this formula, where what is this AG, addendum coefficient of the gear. AG is equal to 1 for this addendum. for the standard addendum. As is equal to 1 for the standard addendum. So what we know that gear ratio G is equal to number of teeth on the gear bata ke number of teeth on the pinion. If the number of teeth on the gear will be minimum, then number of teeth on the pinion also will be minimum. So same formula can be written as gear ratio capital T minimum bata ke small t minimum, that is minimum number of teeth on the gear bata ke minimum number of teeth on the pinion. So minimum number of teeth of the gear can be calculated from here. Then by using the formula of gear ratio, minimum number of teeth on the pinion can be calculated, or also just by using this and this formula we can derive the expression for the minimum number of teeth on the pinion. So what you get, that capital T minimum is equal to G into T minimum. Let us compare this both the equation. Then what you are getting, minimum number of teeth on the pinion is equal to 2 times AZ divided by G. 2 times AZ divided by capital G under root 1 plus 1 by capital G root 1 by capital G plus 2 into sin square 5 minus 1. So a different formula is given in some of the local book. You don't follow that formula. You don't follow this formula. You follow this formula. This formula is very foolproof formula. So if you want to calculate minimum number of teeth on the pinion, you can use this formula, or this will be better that you start to calculate minimum number of teeth first on the gear from this formula. Then from this formula you calculate what is the minimum number of teeth on the pinion. That will be better. That will be better. Okay. So first you calculate minimum number of teeth on the gear from this formula. Then by using this gear ratio formula, you can calculate minimum number of teeth on the pinion, or directly from this formula you can calculate what is the minimum number of teeth on the pinion from this formula. Sometimes they are asking what is the maximum addendum to avoid the interference. So this is the intermediate formula. This is also very important. That is also sometimes needed. So I will recommend you to remember this formula also. So this maximum addendum of the gear can be calculated from this formula as m into capital T divided by 2 inside a big bracket under root 1 plus 1 by z plus 2 sin square 5 outside the under root minus 1. So this maximum addendum of the gear can be calculated from here. So one thing I want to explain here, that for the general meshing of the gear, that is in between the limiting point of interference, addendum of the gear and the pinion will be same. There is no doubt. But to avoid the interference, you can see that addendum circle radius of the gear has reached the limiting point, that addendum circle radius of this pinion has not reached up to the point. Means what? To avoid the interference at the root of pinion, at the root of gear and the tip of pinion, that should reach up to the point here. Means what I want to see, that to avoid the interference, maximum addendum of the gear and maximum addendum of the pinion will be different. So generally maximum addendum of the pinion is greater than or equal to maximum addendum of the gear. So same thing I have concluded here. So what we have concluded, so I have written here, maximum addendum of gear and pinion to avoid the interference at any places will be same. मतलब कहीं पे भी ना हो उसके लिए. But to avoid the interference between the tip of the gear and the flank of the pinion, maximum addendum of the gear is given by this formula. To avoid the interference between the tip of the pinion and the flank of the gear, maximum addendum of the pinion can be found from this formula. But this is useless. This is useless because if already interference has started at the tip of gear and the root of pinion, so there is no question that addendum will start from the tip of pinion and so. Okay. Thank you very much.